Hi, welcome back to LeetCode. Today I'm going to discuss LeetCode problem 951, flip equivalent binary trees. So first of all, I will discuss the problem statement. Then I will see some example how we're getting the output, expect output, and then actually we will share the intuition and recursive approach also. Then we'll go to the C++ code. Okay, and then we will calculate the time velocity, space velocity for the code for this code. Now what is the problem statement? Problem statement is that for a binary tree T, we can define a flip operation as follows. Choose any node, okay, and swipe the left child and right child subtrees. That means we have any tree, binary tree. This is suppose a binary tree 1, 2, 3, 4, 5. So if I call swipe here, okay, then what will be the tree after the modified tree? 1 will be again here, it's no problem, but right child subtree will be flipped with the left child subtree. So 3 will in the left side. Now 3 node 3 will be in the left side and 2 will be at the right side, and 4 will be again same. They will not be changed. Only node 1's left side and right side will be changed, and below that all will be same. Like child of 2, left child is 4 and right child is 5. This will be again same. Okay, and if you call again this flip operation for this node 2, then 5 will be now left child, then 4 will be the right child. Okay, so this is actually flip operation. Now a binary tree X is flip equivalent to binary tree Y if and only if we can make X equal to Y after some number of flip operation. Okay, so given the roots of two binary trees, root 1 and root 2, return true if two trees are flip equivalent or false otherwise. Now what they mention that we'll actually have two trees. Suppose for this example, first example is 1, 2, 3, then 4, then 5, then 6, then 5 have actually 2 child, 7 and 8. 7 and 8. Okay, this is one tree 1. Another tree actually present, so its structure is usually 1, 3, 2, 6, 4, 5, 8, 7. Okay, now we have to check that this is actually equivalent or not, flip equivalent. So here actually both for root both are actually same. So till this node we are actually equivalent, we can say actually. Now go to the next child. Next left child is true 2, and here actually it is 3. Correct. Now can I actually achieve, like can I actually place node 3 here actually? How can we check? If I check the, okay, if I call flip function to my parent, then what will actually happen for this level? It will happen node 1 will be again same, and 3 will be left child will be now, and 2 will be the right child, and 3 actually have 6 as a left child. Okay, and these actually have 4, 5, 5 actually have 2 child, 7 and 8. Okay, now if I call the flip function for node 1, then actually our tree modified tree is it is, and this is actually the tree 2, another tree that actually comparing the equivalent or not. Now actually check that I actually have 3 here, and here actually I have also 3 here, correct? So it's okay. Now here actually I have 2, here actually I have 2 as a right child. Now go to the next level, 6 here. 6 it is present as a left child, but here actually no 6 is present, correct? So can I actually achieve this? If I will call the flip function, I will do the flip operation, then what will happen? Our this will be changed to what? This will be now 6 will be at the right child. So now I'll check what is the left child of this node 3. No left child. This tree 2 also, another tree 2 also do not have any left child. Okay, no problem. Note the right child. What is the right child value? 6. Here also what is the right child value? 6 again. Both are same. Okay, so this is actually equivalent till now. Now go to this node 2. So what is the left child? 4. Okay, this is actually left child is 4. Okay, no problem. What is the right child? 5. Here also right child is 5. Here is 5. So till now this is actually equivalent. Now come to node 7. Suppose. So what will check? Okay, this left child value is 7. What is the left child value of this another tree 2? 8. Both are not same. So I will check, okay, after calling this flip function, can I actually achieve this? So I will do the flip function here. So what will be the now value? Now value will be, here will be 8 and this will be 7. Now what is left child value? 8. Here again it is same, left child value is 8. What is the right child value? 7. Here is the right child value 7. So both are actually same. So you can actually check that we can actually achieve this the actual another tree 2 after by some calling some flip operation, correct? So that you can check in this I have actually 1, similar this also I have 1, here also I have 3, here also I have actually 3, here also I have 2, here also I have actually 2, here actually right child as I have 6, here also right child I have a 6. Similarly for 4, similarly for 5, 4, 5. So 5 actually 2 child, left child is 8, right child here it also have 8, here also it is right child is 7, here right child is 7, correct? So that's why I will return actually here actually I can say actually return true, correct? It is clear. Now suppose this actually our tree look like 1 3 2, this is tree 1 and tree 2 actually is 2 1. This tree is equivalent? No. First of all, our root value is actually different. So easily I can actually say that the root value is not same. So that's why I can actually return false. Now actually I have actually another tree 1 2 3, but here actually I actually have 3 4. Okay. So first of all, what I'll do, I will check the root value is same or not. Okay, root value is same. So I'll check what is the left child value? 2. What is right child value? 3. So here is the for this tree 2. What is the left child value? Left child value is 3. What is the right child value? 4. So both are not same. Left child value is 2, here actually 3. So these two are not same, and these 3 and 4 are not same. So I'll check, okay, without no swiping, or actually left child and right child is not same. So I will try to swipe this. So after swiping, what will be the tree structure? 1 3 2, and this is again 1 3 4. This will be same because we are not call, we will call the swipe for one tree only. So now you can check, is this still same or not after flipping? So you can check, this is 3, this is 3. Okay, what is the right child value? True 2, here actually 4. So this is not same. That time actually we have to return false here, correct? Normally without no swiping we are also not same, and after swiping also we are not getting the same. So that's why I have to return false. We don't need to go to the actually below this level. Got it? So what is the recursive approach? So first what we'll do, what actually you need, suppose for this example I will have two pointer, one for root 1, another for root 2, correct? So first of all do that our root value is same or not. If root value is not same, that time I can return false. If it is same, root value is same, then what I will do, I will check what is the left child value of this tree 1 and what is the left child value of this tree 2. So this is actually 3 and this is 3. This is actually same. Okay. And what is the right child value? Here for it is, this is 2 and this is for actually is 4. Okay. So I'll check, okay, this is not same. I return false. For after for the flow of, if I don't call any flip operation. Another is, if I call the flip operation, then what will happen? 4 will come here and 3 will be here, correct? So I'll check what is the left child value for this tree 1 this is 3. What is the left child value of after flipping? 4. Okay, and this value, right child value will be 2, and the right child value after flipping it is 3. Got it? So you can check again, this is not same. So both is actually we are without flipping and with flipping, both are actually not same. We are not getting the same value, so that time I have to return false. But somehow after this, for this example 1, I have shown you that somehow yes, you can check actually here. We have called flip operation here. If we call the flip operation here, then actually we are getting the equivalent this level 3 and 2, 3 as a left child and 2 as a right child. Correct. This is optional. But for this 2, node 2, we are not calling the flip operation, but we are getting the same equivalent child, like 4 as a left child and 5 as a right child. Here also 4 is a left child and 5 is a right child. Okay. Then we are going to this, whenever we are going to this 5, node 5, that time we check what is the left child value, what is the right child value. Left child value is 8 and right child value is 7. Correct. Then we are calling the flip operation, because ultimately value was 7 and 8. This is actually modified value, that's why actually value was 7 and 8. So we are calling the flip operation here actually for the parent node 5. Got it? So we actually have two flow. One flow is for without for any node I can actually swipe that child node or flip the child node, and another flow is we are not going to swipe this. So suppose for this structure 1 2 3 4 5, okay, so for here actually I can actually call the swipe, otherwise we don't call the I will not call the swipe function. So if I don't call the swipe function, so this will be a tree again, and if I call the flip up function, then what will be the tree? 1 3 2, this will be 4 5. Okay, now for this node 2 I can call the flip function, and I don't want to call the flip function. Here actually I have not called this, so this will be again same. Okay, now suppose I actually call the flip function here. So what will be the tree look like? 1 2 5 4, and this will be 3 again. And for this node here actually do not need to actually call the flip function, because only there is no left or right child. So here actually for this node 2 I can call the flip function, and I don't want to call the flip function. Here actually suppose you don't call the flip function, so this will your tree look like. And if I call the flip function, then what will your tree look like? 1 3 2, this will be 5, this will be 4. Correct? You can check these all 4 tree are actually possible. 4 different kind of tree. This is one structure, this is second structure, this is third structure, this is fourth structure. So I have to, and another tree that actually given, tree 2, can be matched with 1 2 3 4, any one of these. So that's why I have to check the all possibilities, like we are matching with this or not, we can matching on this or not, we are matching with this or not. Okay, so that's why this we also create two flow. One actually for flow actually we are calling the we are not calling the flip operation, don't flip. Another is flip it. Okay, now go to the actual code, then it will be easy. So first of all you check if a root pointer, root 1 and root 2, both pointer is same, that means what? We are actually pointing ultimately the same tree. So that's what we need to check the below level. Correct? So that's why this is object level, right? Address level. Both are pointing to the same node, same memory address. This is both are pointer. See, pointing to the same address, that means what? The child below the level also will be same. So that's why return true. If what can be happen? Our root value is not same. So one situation can be happen that our root 1 is null and root 2 is null. Any one of this, or both are actually present, but value is not same. This value, whatever the root 1 value and root 2 value, not same. That time return false. That means what? This 1 2, this is 3 4, this is 3 4. Below the level 3 and 4 left child right child both are same, but at root level this actually have value 1, this value 2. So these are not same, that's why I'm checking. So if this root 1 value and root 2 value is same or not. If it's not same, that time we don't need to check the below the level. Just from here actually return false. Else what will happen? Suppose both actually any one of these actually null. Suppose this actually happen. So for this node, do I have any pointer in this tree 1? No, because there is no node. So here it will come as a null. Here actually we will get another node pointer. So that's why I will check if there is no actually node. That means any one of these is null, root 1 or root 2 pointer. So that time return false because we do not have any node on that position. So that's why if any one of these, root 1 is equal to null or root 2 is equal to null, return false. And if both are null, this can be happen that for this case, here actually I do not have any node, here also I do not have any node, but that will be handled by here. Both are actually null, this will be null, this will be null. So that's why both are null, that time return true. Correct. Now come to this root node value is same. This is sure. Here actually I have checked this. Correct. This value is same. I actually confirm that. Now we'll check. Okay, do I need to flip or not? So first of all, I'll check. I will not call the flip operation. Then what will happen? The left child value of this tree 1 and what is the left child value of this tree 2, both will be same. So that's why I'm calling this again, this function, this recursively. We're passing the left child value both the same. Here also I'm passing the 2, here also passing the 3. Okay, and similarly for right child I'm passing the same, root 1 dot right, these 2, and this I'm passing 2 3, and here will be passing 3 2. Okay, this is for no swipe. Okay, and again what is the another actually can be possible after calling the swipe function or flip function or flip operation. So again I will call this is for one condition. You can check. I have actually this will return true or false. This after no swipe, this tree is equivalent or not ultimately. So this is one bracket, inside a bracket. Another bracket is what? I am calling the flip operation. Then actually we are getting the true or false, equivalent or not. So that time this recursive same function we are calling. We are passing the left as 2 and right as a 2 again, and this we are passing 3 and this as 3. You can check what is the actually root 1 left value. Root 1 left value is 2. Okay, we are passing actually ultimately 2. And what is the root 2 right value? Root 2, this is root 2, right value is 2 again. Okay, now we are calling what is the flip equivalent function. We are passing the root 1 right value. Root 1 right value is 3, this 3, and root 2 left value is 3. Okay, we are passing 3. So both are actually equivalent. Right, ultimately I will return here from this I will get false, and here actually I get the true. Got it? So I have actually taken the OR, any one of this flow actually I got the equivalent, so that time return true. So that's why I have taken the OR value. You can check here actually I have added one OR value, OR operation. So any one of this flow is I am getting the equivalent, so that time return true. And here actually I have taken AND. Why AND? Between these two left subtree and right subtree, because one subtree is suppose true, but another subtree, right subtree, is getting suppose false. That means what? When this is not equivalent. So this is the ultimate. This suppose 1 2 3 4 5, and this is suppose 1 2 3. Okay, this is suppose 4 5, and this is we are getting 6. So this actually till this are same equivalent, till also both are equivalent. Here also this subtree also return true. Okay, but this node 3 will return false. Why false? Because this actually I have extra node 6, but here actually we don't have any node 6, so that time it will return actually false. Correct? Now this is actually equivalent. This subtree is you are getting the equivalent. You can check. Both actually have parent 2, left child 4, right child 5. correct? But this actually is equivalent, no. So that's why ultimately whole tree will be not equivalent. If any another position part of the tree is not equivalent, that means whole tree is not equivalent. So that's why when you are getting this is actually false. Any of this false, true and false. Ultimately this is actually false. That's why I'm taking the AND operation. Got it? I am taking the between any subtree, between any one tree, we are taking the AND value, and between any two different tree modified, like one actually we are calling the flip operation, and another is not calling the flip. That time both are actually two different tree. Correct? So that's why here actually what is the answer? These are just effect to the this tree also, another tree. Because suppose this is true equivalent and this is false, but okay, we also go through this tree only. It is clear? It is actually short. The code is very short actually. So now it is clear. If it is clear, then please like the video, and if you have any doubt, you can comment on that. Okay, if you not yet subscribed, please subscribe the channel. Now come to the time study part. Time study what? We are actually recursively calling each node, root left child or right child, in this way. So I will actually visit if suppose in the tree I actually have n nodes, then I will visit n times. N times means each node only once. You can check we are visiting each node only once, correct? Suppose in 1 actually I have, so I will check the late 3 and 4 in this way. We are not again visiting 1 again. So that's why the time will be big of n if we have in the tree actually have n nodes. And what is the space count study? Here actually you can check we are actually calling this recursive function flipEquivalent. So this actually, if our tree actually skewed tree, suppose this is actually the tree structure in this way. So in this actually our recursion stack, this flipEquivalent function will go up to depth n if there is n nodes. So that time the space count will be big of n. Got it? This is actually skewed tree. Okay, so it's clear, right?